A single ton of sand comes at a price of $30, and when heated to 400 degrees, it stores enough energy to keep a home warm for 3 entire days. Unlike other storage methods, it never wears out and never freezes. In 2022, engineers in Finland demonstrated this remarkable principle by heating an entire town through the harsh Arctic winter using sand held in a massive steel silo. The physics behind it isn't new. Persian engineers had mastered this technique thousands of years ago. By the end of this story, you'll understand why this technology disappeared in America and how one could be built today. Beneath every house, the earth maintains a steady temperature, but sand has a unique property that ordinary soil lacks. When heated, sand can reach temperatures high enough to boil water multiple times over without the need for a pressurized container, exotic chemicals, or fear of freezing. Its underlying science is astonishingly simple, almost like a loophole in nature itself. Sand has a specific heat capacity of about 0.8 kilojoules per kilogram per degree Celsius. Water, by comparison, holds roughly 5 times more energy per kilogram. At first glance, water seems superior, but the situation changes dramatically when practical limits are considered. Water boils at 100 degrees Celsius. To heat it beyond that requires pressure vessels, specialized industrial machinery, and expensive safety systems. Sand, on the other hand, can be heated to 600 or even 1,000 degrees Celsius and simply remain stable, with no phase changes, no risk of pressure buildup, and no inherent danger. At these extreme temperatures, sand outperforms water in terms of usable heat storage. Consider the numbers. 1 cubic meter of dry silica sand heated from 20 degrees to 200 degrees Celsius can hold roughly 67 kilowatt hours of thermal energy. That amount is enough to heat a modest, well-insulated home for 3 days. Depending on local availability, sand costs between $30 and $80 per ton. Contrast that with lithium battery storage, which ranges from $300 to $600 per kilowatt hour. The gap is staggering. Mere pennies per kilowatt hour for sand versus hundreds of dollars for batteries. Sand doesn't degrade. A properly constructed sand storage system could theoretically last over 50 years. It is chemically inert, poses no fire risk, emits no toxic gases, produces no hazardous waste, requires no rare earth mining, and depends on no fragile global supply chains. Simply put, it stores heat and returns it reliably, generation after generation. Engineers refer to this approach as sensible heat storage. Heat is deposited, stored, and later retrieved without any chemical reaction, phase change, or moving components within the medium. Research published in 2025 confirms that sand can provide high-capacity, long-duration thermal storage even at extreme temperatures. When paired with renewable electricity, it remains cost-competitive with fossil fuel heating solutions for large-scale applications. The principle is so fundamental that ancient civilizations discovered it millennia before thermodynamics was ever formalized. In ancient Rome, 2,000 years ago, engineers constructed buildings capable of warming entire spaces from beneath the floors using a system called the hypocaust. Hot air generated by a wood furnace flowed under raised stone floors and through hollow clay walls, spreading warmth throughout every room. The baths at Cacalla in Rome, the Great Bath Complex at Bath in England, and the city of Timgat in Algeria all employed this method. These early engineers did not simply burn fuel continuously. The real innovation lay in the thermal mass. Stone, brick, sand, and clay beneath the floors absorbed immense amounts of heat during combustion. Once the fire subsided, the mass continued radiating warmth for hours. In essence, the building itself acted as a battery. During medieval times in Northern Europe, this concept evolved into even more sophisticated systems. Underground furnaces were topped with heavy granite stones that, once heated, could release warmth for days from a single firing. One fire could keep a monastery in 14th century Livonia cozy for 48 hours or more, even in the midst of snowstorms and fierce winds. Historian Klaus Bingenheimer estimated in his landmark 1998 study that at least 500 hypocaust systems existed across Europe during this period, with 154 specifically designed for heat storage. Further research has since uncovered many additional examples. These systems represented a fusion of Roman heat storage techniques with traditions from indigenous populations in present-day Finland, Estonia, and Latvia, who had perfected sauna heating using similar methods for centuries. Across the Pacific, Korea developed the Andal system, which delivered heat from cooking fires through channels beneath stone and clay floors, maintaining interior temperatures between 64 and 72 degrees Fahrenheit during the harshest winters and even through hot summers. Historical records in the Samguk Sagi detail these systems sustaining comfort long before modern HVAC existed. In the deserts of ancient Persia, engineers applied the same principle in reverse. Thick mud brick walls and dense clay floors absorbed scorching daytime heat and radiated it through frigid nights when temperatures could drop by 40 degrees Celsius within hours. Villages in present-day Iran and Afghanistan still bear these architectural marks. Meter-thick walls, packed earth floors, buildings designed to breathe with the sun's cycle. Romans, medieval Europeans, Koreans, Persians, and Scandinavian indigenous peoples, all confronted with extreme temperatures, converged on the same solution. They stored heat in massive materials and allowed it to be released slowly, trusting physics to do the work. Across 5 continents and 3 millennia, this approach appeared independently time and again. Yet within a single century, this solution vanished entirely from Western construction practices. In 2016, a Finnish engineering student named Tommi Aronen was investigating water-based energy storage for his master's thesis. While studying traditional Finnish stone and sand fireplaces, which could hold heat for days from a single firing, he experienced a revelation. The answer was not water or chemicals, it was sand. 6 years later, the BBC reported the breakthrough to the world. In the small town of Kankapaa, Finland, a 7-meter-tall, 4-meter-wide steel silo housed 100 tons of locally sourced sand, demonstrating the practicality of this ancient concept on a modern scale. The first commercial sand battery in history was constructed by Aronen's company, Polaroid Energy. This pioneering installation provided 200 kilowatts of thermal output while storing 8 megawatt hours of energy. It tied directly into the town's district heating system, delivering warmth to residences, businesses, and even the municipal swimming pool throughout the long winter. While temperatures outside dropped far below freezing, the building remained comfortably heated, fueled entirely by sand. The engineering behind it is astonishingly straightforward. Electricity from the grid or nearby renewable sources powers a resistance heater housed inside an insulated steel container. A fan circulates hot air through the sand, raising its temperature to as high as 600 degrees Celsius. Surrounding insulation retains this heat for hours or even months, depending on the scale of the installation. When demand arises, a heat exchanger channels warmth from the sand into the district heating water network, achieving up to 99% heat recovery. Kankapaa, however, was just the beginning. In 2024, Polar Night Energy deployed a far larger sand battery in Pornin, Finland. Imagine a steel cylinder 13 meters tall and 15 meters in diameter, filled with 2,000 tons of crushed soapstone. This colossal battery generates 1 megawatt of thermal energy and stores 100 megawatt hours, 10 times the capacity of the original. Engineers estimate that it could reduce Pornin's carbon emissions by 70%. During summer months, when renewable power floods the grid, this single installation can store nearly a month's worth of the town's heating needs. In winter, it can supply close to a full week of heat. Aronen explained that cities such as Tampere already operate district heating networks, circulating hot water through entire neighborhoods. His sand batteries integrate directly with this infrastructure, enabling communities to transition to renewable heat, both rapidly and cost-effectively. The innovation earned Polar Night Energy a spot on Time magazine's list of the best inventions of 2025, and the company shows no sign of slowing. Plans are in place to construct a 250 megawatt-hour sand battery in Lahti, Finland, beginning early in 2026. Supported by a grant from the Finnish government agency Business Finland, this ambitious project aims to convert stored thermal energy back into electricity. The expected electrical efficiency is around 30 to 35%, and when applied to combined heat and power production, the overall efficiency could reach 90%. By 2026, sand will be generating electricity in a scale never before documented. Thousands of tons of heated sand providing warmth for thousands of homes, verified through independent research across multiple Finnish winters. The technology has proven itself at laboratory, household, and municipal scales. This raises an unavoidable question: why has none of this been adopted in the United States? Open the International Residential Code and look for any section permitting sand-based thermal storage in home heating systems. There is nothing. The code is centered on mechanical devices, furnaces, heat pumps, air handlers, and ductwork routed through attics or crawl spaces. Compliance pathways assume manufactured appliances in utility closets, consuming gas or electricity on demand. A steel container filled with heated sand does not conform to this template, and if it does not fit, approval is impossible. Picture a contractor presenting blueprints to a county building office that include a sand battery in a client's garage. The inspector flips through the code looking for guidance and finds nothing. There's no framework for evaluating solid media thermal storage, no standard for testing, no mechanism for approval. The plans are rejected, not because the technology failed, but because the procedures for verifying it do not exist. Standard 90. 1, published by Asher, establishes minimum energy efficiency requirements for buildings throughout the United States. Its calculations assume conventional mechanical heating and cooling as the baseline. A sand battery that warms a home with stored renewable energy cannot earn a compliance score because the formulas were never designed to measure it. The technology remains invisible to the regulatory system. It is not prohibited, it is merely unacknowledged. In practice, the result is the same. The International Energy Conservation Code offers 0 credit for passive or solid media thermal storage. Builders receive no incentive to adopt systems that eliminate traditional heating equipment. The regulatory structure rewards machines and penalizes simplicity. Now, follow the financial currents, and the picture becomes clear. The American residential HVAC market generates tens of billions of dollars annually from equipment sales, installation contracts, maintenance agreements, and refrigerant charges. More than 45% of electricity consumed in American buildings is used for space heating and cooling. This enormous flow of revenue supports manufacturers, distributors, contractors, and utility companies every month. Every sand battery installed in a home would eliminate a furnace that is never sold, a compressor that is never replaced, a service contract that is never signed, and a refrigerant recharge that is never needed. Walk through any suburban area in Houston, Chicago, or Phoenix, and you'll see HVAC units on rooftops and concrete pads beside every home. Each represents a recurring income stream that a heap of heated sand would permanently remove. Imagine executives examining market projections on glowing screens, lobbyists moving through government hallways with briefcases full of position papers, and trade group representatives sitting on committees that dictate which heating technologies Americans may install. The system does not suppress innovation through conspiracy. It protects existing revenue by maintaining inertia. Codes written by industry insiders naturally favor industry products. Technologies that make those products unnecessary never enter the code, not because they were rejected, but because no one proposed them. Finland succeeded partly because its infrastructure was ready. District heating networks already circulate hot water through entire neighborhoods, providing a natural channel for centralized thermal storage. By contrast, the American model fragments heating. Each home functions as an isolated thermal island with its own furnace, its own therms, and its own monthly bill. There is no shared system to integrate a community sand battery. The network was designed to sell individual machines to individual homeowners, not to facilitate shared solutions at scale. Codes do not recognize it. Industry does not sell it. Infrastructure cannot support it. Yet none of this alters the laws of physics. And physics tells us clearly, you can build one yourself. Constructing a simple sand battery is surprisingly affordable. A 200-liter steel drum filled with dry silica sand, combined with standard resistive heating elements, costs roughly $180 to $320 in materials. This price covers the drum itself, the sand, the heating elements, mineral wool insulation, a temperature controller, and a small inline fan. For larger, custom-built systems capable of storing 50 kilowatt hours or more, costs range from $500 to $1,500, depending on the quality of insulation and the design of the heat exchanger. Remarkably, the sand alone costs less than $10 for a 200-liter drum. Charging the system is elegantly simple. Solar photovoltaic panels can be wired directly to resistive elements, converting sunlight into heat without the need for an inverter. There is no battery management electronics or sophisticated controllers required. Sunlight turns into electricity becomes heat, and the sand stores it. When sunlight is insufficient, off-peak electricity from the grid can serve as an alternative or supplement for cloudy days. A 2 to 4 kilowatt solar array is enough to raise the temperature of a 200-liter drum of sand toward 150 degrees Celsius over a few sunny days. Extracting that heat from the sand to warm a living space requires a heat exchanger. The simplest method uses air. A low wattage fan pushes air through metal pipes embedded in the hot sand. The air absorbs the heat from the pipes and flows into the room via ducting or directly through a vent. On a household scale, this provides 500 watts to 2 kilowatts of continuous heating, sufficient for steady background warmth in a well-insulated space or to preheat domestic hot water before it reaches a conventional water heater. For anyone constructing their first system, maintaining temperatures below 150 degrees Celsius is critical for safety. Operating below this threshold allows the use of standard wiring, insulation, and plumbing fittings. Exceeding 200 degrees Celsius requires high-temperature wiring, refractory materials, and specialized components, significantly increasing both cost and complexity. The sand must be completely dry. This is non-negotiable. Moisture in sand at high temperatures turns to steam, generating dangerous pressure within a closed container. Using dry silica sand eliminates this risk entirely. To prepare, spread the sand on a metal sheet under direct sunlight for 2 full days, or bake it in batches in a standard oven at 200 degrees Celsius for 1 hour per batch. Always test a small sealed sample by heating it and checking for condensation inside the container. Temperature monitoring with automatic shutoff is essential. A basic thermocouple connected to a relay controller that cuts power at the target temperature costs under $50. Place the storage unit in a detached workshop, garage, or an outdoor buried installation. Never operate it inside the main living area at high temperatures. Basic electrical safety and common sense apply as they would with any other heating appliance. Insulation is what separates a functional sand battery from a costly disappointment. A poorly insulated drum loses its stored energy within hours. Wrapping it in mineral wool with an outer layer of rigid foam board creates an efficient thermal barrier. Aim for at least 150 millimeters of insulation on all sides, including the top and bottom. Every additional millimeter increases the duration your sand retains heat. The system is modular by nature. Start with a single drum to test the concept. Measure charge times, discharge rates, and overnight heat loss to understand your setup's behavior. Then add a second drum, then a third. Multiple drums can connect in parallel, feeding warm air into a shared duct. This allows scaling from heating a small workshop to supplementing an entire home, one drum at a time. A single 200-liter drum of sand heated to 150 degrees Celsius stores roughly 7 to 8 kilowatt hours of thermal energy. That's enough for a full day of supplemental heating in a well-insulated home. 4 drums provide 3 to 4 days of thermal buffer, sufficient to ride out a cold snap solely on stored solar energy. For homes with existing hydronic systems, such as radiators or underfloor loops, a simple air-to-water heat exchanger lets the sand battery integrate seamlessly. Hot air from the sand transfers heat to circulating water, which then warms radiators or floors, requiring no modification to the current distribution system. Maintained properly, the setup lasts for decades. The sand itself does not degrade or lose capacity. 50 years from now, it will remain the same as the day it was first poured in. Sand-based thermal energy storage reaches efficiencies near 90% when paired with low-cost renewable electricity. It achieves a levelized cost of heat that competes with natural gas or propane. These are not startup projections. They are documented in peer-reviewed engineering journals from 2025. The physics behind it requires no government subsidies or breakthroughs. All it takes is building a container, filling it with sand, and applying a heat source. In Kankapaa, a steel silo full of sand warms a town through the Arctic night. In Pornin, 2,000 tons of crushed stone cut emissions by 70% while families sleep comfortably. In Ladi, engineers are preparing to demonstrate that heated sand can generate electricity and feed it back into the grid. Across Europe and America, workshops and garages host builders proving every weekend that this concept functions at any scale. Ancient civilizations understood the principle. Romans stacked stones beneath marble floors, letting thermal mass carry warmth through Mediterranean nights. Medieval monks fired granite hypocausts once and heated stone halls for days. Korean families mastered it for 3,000 years before Western architects largely forgot it. This knowledge endured every empire and dark age because physics does not care about marketing, regulatory capture, or furnace manufacturers' quarterly reports. Sand is Earth's most abundant mineral. It has absorbed sunlight and released heat through nights for 4.5 billion years, storing thermal energy long before life existed. It retained heat beneath Roman bathhouses, Korean farmhouses, and traditional saunas. Today, it keeps towns in Finland warm during the darkest winters, powered entirely by last summer's sunlight. Codes will eventually adapt, but you don't need to wait. You don't require a manufacturer's approval to fill a drum with sand and connect a solar panel to a heating element. The knowledge is accessible. The materials are available at any local hardware store. The sun is shining. The sand has been waiting as it always has.